This is part 7 of a series on artificial neural network. In this video, we will look at the linear and nonlinear regression. This video was produced in Korean and translated into English. My voice was generated by AI, text-to-speech. In the last video, we wrote a code to implement classification using an artificial neural network. In this video, we will write a code to implement a regression model. A single-layer perceptron can be used to implement a linear regression model, and a multi-layer perceptron can be used to implement a nonlinear regression model. In the machine learning, we implemented the nonlinear regression model using weighted linear regression or support vector regressor. Weighted linear regression model takes a long time to make predictions because it is a lazy learner. And support vector regressor model required the use of a kernel function. Using artificial neural networks, nonlinear regression models can be easily implemented by simply changing the loss function and the activation function in the output layer. The output layer uses a linear activation function, and the hidden layer uses nonlinear activation function, such as sigmoid, hyperbolic tangent, ReLU. And mean squared error, MSE, is used as the loss function. Now let's implement a single-layered perceptron to perform linear regression. We will use the gradient descent function we created before. As mentioned before, to calculate the gradient accurately, we need to use automatic differentiation. However, here we use numerical differentiation to approximate the gradient to better understand how ANNs fundamentally work. We will take a closer look at gradient descent using automatic differentiation in the error backpropagation algorithm later. The data we will use is like this. This is a dataset mixed with Gaussian noise along the straight line, y equals 0.5x plus 0.3. We want to learn from this data to predict the equation of the original line, generate training data, validation data, and test data. Check the data visually. This is the result from this code. Now we create a single-layered neural network model like this. Since the data is one-dimensional, that is, has only one feature, there is only one neuron in the input layer. There is also one neuron in the output layer. The structure of this neural network is very simple like this. When one-dimensional data X is input, Y is output. The connection weight between the input layer and the output layer is WO. This is the slope of the regression line. And the bias is BO, which is the intercept of the regression line. The learning rate alpha is set to 0.01. And the constant h for numerical differentiation was set to 10 to the power of -4. Next, we initialize the parameters. WO is a 1-by-1 matrix, and BO is also a 1-by-1 matrix. The weight matrix WO is randomly initialized, and the bias matrix BO is initialized to 0. The parameter list contains the matrices WO and BO. Next, we write a function that uses this formula to calculate the mean squared error loss. Since this is a regression problem, mean squared error is used. Next, we write a function to calculate the output from this neural network. This is the prediction process. When you input data X into this neural network, the output is calculated using this formula. P0 is the matrix WO, and P1 is the matrix BO. Next, we write a function that performs the training process. Repeat the following process the given number of times. Input the training data x and the validation data xval into the current neural network and measure the loss. The parameters of the initial neural network are random values that have not yet been trained. Next, we iteratively update the parameters using mini-batch gradient descent. Create a subset of a given batch size, and perform the gradient descent on this subset. Then the parameters will be updated once. By repeating this process, the parameters are continuously updated, and the neural network is gradually trained. Now we call the train function. The number of iterations was set to 100, and the batch size was set to 50. Visually see the loss history measured during training. Next, we visually examine the estimated regression line. Let's check the results. As the iteration progresses, you can see that the loss of the training and validation data gradually decreases. Visualizing this, it looks like this. If you see the losses gradually decreasing, you can assume that the parameters have been updated to their optimal values. The estimated slope and intercept are as follows. The equation of the original straight line is like this, and the estimated regression line is like this. These two are quite similar, and the estimated regression line looks like this. A single-layer neural network allows you to implement a linear regression model in this way. Let's run this code. The results came out like this. Now, let's implement a two-layered neural network model to perform nonlinear regression. Here we will also use the gradient descent function we created before. The data we will use is like this. This is a data set mixed with Gaussian noise along a sine curve. We want to use this data to estimate a nonlinear regression curve like this. Generate training data, validation data, and test data. And we look at the data visually. Now let's create a two-layer neural network model like this. Since this is one-dimensional data, the number of neurons in the input layer is 1. And since the output is also one-dimensional, the number of neurons in the output layer is also 1. We used 16 neurons in the hidden layer. We set the learning rate alpha to 0.01, and we set the constant h for numerical differentiation to 10 to the power of -4. Next, we initialize the parameters of this neural network. The connection weights, WH, between the input layer and the hidden layer is a 1/16 matrix. And the bias, BH, is also a 1/16 matrix. The connection weights, WO, between the hidden layer and the output layer is a 16/1 matrix. And the bias, BO, is a 1/1 matrix. WH and WO are initialized to random values, and BH and BO are initialized to 0. The parameter list contains these matrices. Next, we write a function that computes the output of this neural network. This is the prediction process. The output of this neural network is calculated by this formula. P0 is the matrix WH, and P1 is the matrix BH. P2 is the matrix WO, and P3 is the matrix BO. We used a hyperbolic tangent activation function in the hidden layer. In this case, we use this because it performs better than using ReLU. Next, we write a function that performs the training process. This is identical to the previous code. We call the train function. We set the number of iterations to 1,000 and set the batch size to 50. And visually check the loss history and estimation curve. Let's check the results. As the iterations progress, the loss on both training and validation data decreases like this. And the estimated regression curve looks like this. The original sine curve is well estimated. In this way, we can easily implement nonlinear regression models using multi-layer neural networks. Let's run this code. The results came out like this. So far, we have looked at the basics of artificial neural networks through a total of 7 videos.